Oh, excuse me. Good morning. So today I'm going to go through a couple free response questions on the 2019 free response test. I've shared this link with you in my email. So I'm just asking that you I'll go through multiple free response questions today, and I'd ask that you kind of either pause the video or try these by yourselves, or certainly at the very least watch the whole thing so you can understand what I'm talking about and what I'm going through. And my plan is to release these videos every single day from here on out. So I'll be kind of constantly going through various free response questions for you guys and going through my thinking, going through what AP is looking for. And yeah, so anyway, so I'm on the 2019 test, like I said, the link's in your email. And I'm going to go through questions 1 and 2. We are going to skip the parts that are related to units 8 and 9. Both of these problems have stuff related to unit 9 that I'll just skip right over. So we won't do the entirety of these things, but the majority of them. All right, so this is the exact format that you can expect to see in the digital format. I imagine they'll keep this all the exact same. Obviously, this will be different, but you can probably expect to see this very similar format for the actual test. So, okay, number 1, the compound urea, which is drawn up above, and H2NCONH2, is widely used in chemical fertilizers. The complete Lewis dot diagram is above. Okay, so there we go. Part A, identify the hybridization of the valence orbitals of the carbon atom in the urea molecule. So here's carbon right in the middle, and they are looking for the hybridization. So hybridization is all based off of the coordination number, and around this carbon we are separating 1, 2, 3 other atoms. So the coordination number is 3, the hybridization is sp2. That's the answer. And that's all they want. They don't want an explanation here. They don't want anything more. Literally, if you have 1, you label it 1A, sp2, boom, you got a point. Okay? B, urea has high solubility in water due in part to its ability to form hydrogen bonds. A urea molecule and 4 water molecules are represented in the box below. Draw draw 1, specifically 1, so don't draw 2 dashed lines to indicate a possible location of a hydrogen bond between a water molecule and a urea molecule. This sounds rather simple because these are waters, that's urea, so it's like, oh, okay, just draw 1 dashed line. But where that dashed line starts and where that dashed line ends really matters, because we want to show, let me go back to where I want to be. We want to show positive and negative attraction, right? So water is polar, these oxygens here are partially negative. In the urea molecule, this nitrogen is partially negative, the hydrogen is partially positive. So when hydrogen bonds form, they always form between the partially negative part of one molecule and the partially positive part of another molecule. So the oxygen is partially negative, this hydrogen is partially positive. This would be an appropriate spot to draw a dashed line. This would be an appropriate spot to draw a dashed line for the same reason. Partially negative oxygen, partially positive hydrogen, and then last but not least over here. What you want to be careful of is showing like 2 positive parts being attracted, right? So I couldn't show that this hydrogen and this hydrogen are attracted because they're both partially positive charged. That's not what we want. The other thing you want to be careful of is making sure that what you're showing is actually a hydrogen bond. Hydrogen bonds occur between hydrogen atoms and then either fluorine, oxygen, or nitrogen on another molecule. So here's hydrogen on one molecule, here's oxygen on another, right? That is a hydrogen bond. So hopefully that kind of makes sense. Part C, this was a little annoying, there's a page break here, but we need this information for question C. So question C is asking us to calculate the concentration, in other words, molarity, of the urea solution, and the information for that solution is given up above. So we have 5.39 grams of the urea, they give us the molar mass, which is nice, we don't have to do that or look that up, and then we have 5 milliliters total of solution. So if we want to find molarity, we just convert our grams into moles, and then take our moles divided by our liters. And that's it. So it's a tiny little factor label problem here, and it's going to look like this. We solve for the moles using the molar mass, take those moles divided by the liters. Again, convert your 5 milliliters into liters. I didn't show that, but we're just dividing by 1,000, and you should get a molarity of 17.9 molar for part C. Part D, they give us a whole bunch of equipment and they show us a whole bunch of stuff, and then okay, so these are the lab questions, okay? These are extremely common. I can all but guarantee that next week Thursday you have a lab question of one of the 2 that you're going to get. So let's see what they're looking for here. The student also determines that the concentration of urea in a saturated solution at 25 degrees Celsius is 19.8 molar. So they've increased the temperature, and the saturated molarity is 19.8. Based on this information, is the dissolution of urea endothermic or exothermic? Justify your answer in terms of Le Chatelier's principle. Okay, so we calculated it at 20, they cranked up the temp to 25, and we have a different molarity. Comparing those molarities, we have, comparing those molarities, we saw that we had 17.9 at 20 degrees Celsius, and now once the temperature has been increased to 25, it's 19.8. So the molarity has gone up, okay? They did give us a reaction in here somewhere. Where are you? Oh, there it is. Right there. So there's a little reaction in here that we want to reference, okay? And essentially, when the molarity increases, right, we are shifting further to the right. The aqueous stuff, because molarity is moles per liter. It's implying an aqueous solution. So we have the molarity increasing. Here's the equilibrium, and the temperature went up. So as the temperature increased, the molarity also increased. Considering Le Chatelier's principle, this implies that the equilibrium is shifting towards the products, so the energy term must be on the reactant side, meaning that this process is endothermic. There's a whole bunch of different ways you can say this. There's a whole bunch of different ways you can phrase this, but at the end of the day, what you need to realize that as temp went up, or as energy increased, we shifted right to increase the molarity, right? So the energy term must be on the left-hand side, the reactant side, which means this is an endothermic process. Part E, this is now the lab, so we got all these lab equipment. So the equipment shown above is provided so that the student can determine the value of the molar heat of solution for urea. Knowing that the specific heat capacity of the solution is 4.18 joules per gram degree Celsius, list the specific measurements that are required to be made during this experiment. So what we're trying to do here is we're trying to figure out how much heat is released or how much heat is used up, right, endo-exo, when we dissolve urea in water. That's what they're asking for, okay? So the way we do that, and you can see a cup, a thermometer, stir rod, the stuff, the balance, the water, the urea, okay? This is a Q equals MC delta T question. So knowing that, all right, we want to use this equation. What do we need to record from the lab to solve for Q? Because really, they're looking for the heat, right? They want the molar heat of solution, meaning how much heat is gained or lost in the process. So if we want to solve for Q, then we should be able to use or find all of the other pieces. The mass we need, so that's something we'd have to measure and record. The change in temperature is something we'd have to measure and record. The specific heat capacity they gave us, right there. So really, what we need is the mass of the water, the mass of the urea, and then the initial and final temperature of what the process is going to be right before and afterwards. So that one's a little abstract. I think when you see the answer, it's like, oh yeah, that makes sense. But I think reading that one on the surface without having any context or without being able to immediately look at the answer is pretty tough, actually. All right, part F, this is Unit 9. Part G, Unit 9, Part H, Unit 9. So none of these are relevant to what we're going to be doing in this year's test, so we're going to skip them. Onward and upward to question 2. All right, answer the following questions relating to the chemistry of halogens. And halogens, again, are the 17th column on the periodic table. So, you know, fluorine, chlorine, bromine, iodine. A, the molecular formulas of diatomic bromine, chlorine, fluorine, and iodine are written below. Circle the formula of the molecule with the longest bond length. Justify your choice. Okay, so this is the other thing you want to be on the lookout for, right? This is a 2-point question. And the reason why it's a 2-point question is because they're not only asking you to identify which one is the correct answer, but they want you to justify why. All right? So you'd get a single point for identifying it correctly, and you'd get another single point for justifying it correctly. So we're looking for the one with the longest bond length. All right? Well, bond length is going to be based on atomic radius. In other words, how big the atoms are. Tinier atoms, like fluorine, can get closer together. Larger atoms, like iodine, are going to be further apart. So the further they are apart, the longer the bond length is going to be. So the correct answer here should be iodine. Okay. And then essentially, we're going to talk about the size of all these atoms to justify our answer. So these are all diatomic molecules that have single bonds, so the answer lies in the size of the atoms. Smaller atoms can get closer together. The largest atoms of the group are iodine, so diatomic iodine should have the longest bond length due to having the largest radius. That's it. I think it's fairly intuitive, I hope. Again, you're talking about measuring the length of a bond, and there are questions that can relate to bond length to bond order. If you remember, bond order is just single, double, or triple bonds, so 1, 2, and 3. And as bond order goes up, the bond length goes down. So a triple bond is shorter than a double bond is shorter than a single bond, and so on and so forth. But that's not what this question is asking about. This question is basically just looking at the size of these atoms, and the bigger ones are going to be further apart and have a longer bond length. B. Using the data above, however, this is Unit 9, so we're going to skip B. Part C. The boiling point of bromine is 332 Kelvin, whereas the boiling point of bromine, or bromine monochloride, whatever you want to call that, is 278. Explain the difference in boiling points in terms of intermolecular forces present between molecules of each substance. So now they want us to justify why bromine's boiling point is higher than this bromine monochloride molecule. So already offhand, we can kind of sort of BS this a little bit. I shouldn't say that, I shouldn't recommend that, but in reality, a higher boiling point means stronger intermolecular forces. Okay, so we already have like sort of the right answer in our back pocket, but we need more than just saying that these are stronger, right? Well, they want to know why. Why are these intermolecular forces of bromine stronger than the intermolecular forces of the other one? Okay, so here's what I have. The reason why bromine has a higher boiling point compared to BrCl is due to the polarizability of bromine. The bromine diatomic molecule has more electrons, it's a larger molecule, and therefore the London dispersion forces would be greater due to this increased in polarizability. Okay, so essentially, when you're talking about intermolecular forces, more electrons, more stuff, more surface area, more space, more size, that's always going to lead to stronger intermolecular forces. All right. The good news is, again, we already knew that bromine had stronger intermolecular forces, right? Because on the surface, if you look at this a little closer, it's actually tough to tell that bromine would have stronger intermolecular forces. And the reason why I say that is because this is two different atoms. So in theory, this would actually have dipole-dipole intermolecular forces, and the bromine would just have nothing but London dispersion. So it's a little dangerous if they didn't give us the answer already. They told us that this has stronger intermolecular forces by giving us the boiling points. So because of that, the type of intermolecular forces has nothing to do with this answer at all. What's going to have to do with this answer, where the difference comes in, is that two bromines is bigger, more electrons, more size, than a bromine and a chlorine. So it's the polarizability that makes this have a higher boiling point. Okay, D, calculate the pressure in the container before equilibrium is established. So we have this equilibrium here. So we're decomposing the BrCl now into the two individual diatomic molecules. We have an enthalpy, which we'll deal with later, but they're asking us if 0.1 moles of the sample is placed in a previously evacuated rigid 2-liter container at 298 Kelvin, eventually the system reaches equilibrium, calculate the pressure. Okay, so we have moles, we have volume, we have temp, and we're asked to solve for pressure. It's an ideal gas law question, PV equals nRT. So we just set it up, plug and chug, and this should be pretty straightforward. We're solving for pressure, we don't know that. They gave us the volume, they gave us the moles. This is the value of R, the ideal gas law constant from your formula packet, which it is in there. And this is the temp. Do some quick little algebra, and you should get a pressure of 1.22 atmospheres. E, write the expression for the equilibrium constant KEQ for the decomposition of BrCl. In other words, set up the equilibrium constant expression. So, here's the reaction. Products over reactants. We have this to the first times that to the first divided by this squared. It looks like this, right down here. And that's all they're looking for E. F, determine the value. Now this is way more involved, okay? There's another sentence in between here that I shouldn't skip. We should really be focused on this because this is going to be what's going to help us solve this thing. So after the system has reached equilibrium, 42% of the original BrCl sample has decomposed. In other words, 42% has turned into the products, which are these two things, and the remaining 58% is still the reactant. Okay? So this is an ice table, which is lots of fun. We have to use some values that they've given us way back in this problem. Okay, not way back, I suppose, right here. But there's two ways to solve this. Okay, because these are all gases, we could totally use pressures. That would be perfectly fine. We know from part D that the pressure in the container is 1.22 atmospheres. So you could use this as your initial value of the BRCL in your ice table. Or if you choose to use molarity, we can also solve for molarity because we have 0.1 moles and 2 liters. So either which way you do this, whether you use the pressures because this is an all gas equilibrium, or whether you use the molarities because it's also available to us, it doesn't matter. You can use either which one. I chose to use molarity. And what I'm doing here then is I'm setting up an ice table for this decomposition. Okay, here's my reaction. My initial molarity is this, and again, that's solved from taking the 0.1 moles divided by the 2 liters, which gives me 0.05 molar. I have an initial molarity of that stuff right there, neither of the two products as it hasn't decomposed yet. I subtract off a value of 2x because of the coefficient. On the product side, this goes up by x and x, and at equilibrium, I get this. Now, we could put this into the equilibrium constant expression right away, but we know how to solve for x already. They told us that 42% of the original is decomposed, meaning 58% is there when it's all said and done. So, at the end here, this should equal 58% of what we originally had, right? Because after I subtract off what decomposes, I should still have 58% left. So 58% of 0.05 ends up being 0.029 if you punch it into a calculator. So I know that my equilibrium value of the BRCL should be 0.029. So I just do a little algebra here. I can solve for x. I know that I had this much originally. I subtracted off a value of 2x, and I know I should have this much at the end, and x ends up being 0.0105. I then take that value of x and plug it in for everything, and these are my equilibrium molarities. I plug those back into the K expression, and again, the K expression is set up like this, so I would have 0.0105, 0.0105, and I just squared that right away. And then I have 0.029 for the product. So reactants, sorry, for the reactant, my bad. So this is the products over the reactants, and then you should get a value of K equal to 0.131. That one's a little more involved. I would strongly recommend you pause the video throughout that. Take a look at my work here. Take a look at the problem again if you have this document up as well. But that's by far the most difficult of these first two problems that I think we've done. That's pretty tough. F. So determine the value of, oh, I'm sorry, we just did F, my bad. G. Calculate the bond energy of the BRCL bond in kilojoules per mole using the enthalpy for the reaction and the information in the following table. So this is a bond energy one. This is directly from Unit 6. And essentially, we do need to remember that as we break bonds, that requires energy, meaning endothermic, positive value. And as we create bonds, that's exothermic, energy gets released. That's really, 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 really important in this problem. And here's what I have. Here's the reaction. Again, we're using the decomposition of this bromine monochloride into bromine and chlorine. And what we know is they gave us the bond energy of bromine, they gave us the bond energy of chlorine, and we also know the enthalpy of the overall reaction. So the overall change in energy here for this process should equal the amount of energy that we put in to break these and the amount of energy we get released when we create these. Again, this term should be positive because we are breaking that bond. These two terms should be negative when we plug them into the expression because we are creating those bonds. So again, you break a bond, positive, it requires energy. You make a bond, negative, energy gets released. Okay, so we set it up. We know the total is 1.6. I know that I have a positive value of 2x from breaking these bonds, And again, that 2 comes in from the fact that we have a coefficient of 2. And the positive term then gets combined with the negative term. The negative term over here is going to be the negative 193, just one of those because there's a coefficient of 1. The negative 243, again, coefficient of 1. So I have the full value of the negative, 2x positive equals 1.6. Do a quick little algebra here, and you should get a value of 219. Now, I put the energy here in kilojoules per mole, and the reason why I did that is because every single other value is in kilojoules per mole. Okay, so I'm just mimicking their label. I could explain how that per mole stuff works, but really just mimic what they've given you, right? If the other 2 bond energies are kilojoules per mole, then your answer should probably also be kilojoules per mole. All right, so that's 1 and 2 on the 2019 test. I'll probably keep going through this 2019 test because, again, this was literally the exact questions that were on the test last year for the students that took it. But yeah, so I'll share this document out. Please feel free to look forward or look further into this test, and again, I'll probably plow through them. I'll probably give you guys some more questions tomorrow. I know tomorrow's not an official school day, but I'll throw them out to you, right? Because I think you're probably in study mode. I hope you're in study mode. So whether you use them tomorrow or not, that's totally up to you. It's certainly not required, but your test is in 1 week, so I imagine that there's probably some motivation to look at some of this stuff. So either way, please let me know if you have any questions, guys. Have a great weekend, and we'll talk to you soon.